Okay, we're going to look at further examples from the week 2-3 rapidly varied flow, specific energy calcs, and in this one we're going to look at the energy in a contraction, EG3, so the fourth tab. Right, the question here is looking at flow in a contraction, so it's got a width of 1, which is wider than width at 2, so the flow is contracting. So the depth, it is either going to drop from Y1 to Y2, or it's going to increase, depending on whether we've got sub or supercritical flow going in. The question, and it's down here on the right, I'm going to move it up to more top here and zoom in a little bit. So the question is saying, well, we've got uniform flow in a 3 metre wide channel, 1.5 metres deep, Manning's N of 0.015 and a slope of 1 in 1,000. So this Manning's N and the slope and the width are essentially there to help us calculate the flow rate, because it says it's uniform flow, so we're going to use Manning's for that. They're not related to the energy calculations. So let's first do that. Well, I've sort of set this up already. I put in the yellow the numbers that we know, and on this right hand side, a part of the Manning's calculation, which we're going to use this formula, we're going to I've put in calculation for A, which is just B times Y, calculation for B, which is just B plus 2Y, and calculation for R, which is just A over P. So having all this data, I should say we've got S is 1 over 1,000 directly in there. We can use the formula for the Manning's using those intermediate calculations. So we've got A times R to the 2/3 times slope S0 to the half, all divided by N. Gives us a flow rate in the channel of 7.83. We're not going to use that Manning's calculation anymore. We're going to stick to the energy calculations for this. There's two questions in this example. Calculate the width of a contracted channel that will cause critical flow at the throat, so at the narrow bit. We're going to have critical flow, that is, we're going to have critical depth at that point. So that's what it's telling you. And then the second part, if the width of contraction is 2 meters, what would be the depth in the throat and the resulting depth upstream at 1? Okay, I'm going to move this out of the way because it's in the calculations already, on the sheet already. So we're going to go straight into doing this calculation. I've shown in here the intermediate things that we've seen on previous sheets. So Q is just, so Q1, little q1, lowercase q1 is Q over B1. Now remember, we're going to have a little lowercase q2 because B2 is not the same as B1, so that's the thing to look out for. Q1, lowercase q1, velocity 1 is just Q1 over Q over the area. Faraud number, we use our Faraud number formula that we've used previously, V over root GY. Critical depth, we use the Q over Q squared over G to the third. It's Q1, so E1, we're just using the energy calculation as normal based on the width we have at that point. Now we're going to calculate E critical. So E critical, remember, we can look at our formula here. Now I've got it in terms of E2, but it's the same for E1. E crit is equal to 3 over 2 Y crit, or Y crit is equal to 2/3 of E crit. Okay, so for E1 crit we can type E1 crit is 2/3 of Y1 crit. So what do we see in the numbers? That the critical energy is 1.3, the actual energy is 1.6. So we know that we're in the top half of the energy curve, so we know that we're in subcritical flow, and proud numbers telling us that as well, that it's less than 1, so we're in subcritical flow. Right, specifically on the question, calculate the width of the contracted channel that will cause critical flow at the throat. Well, what do we have? We have our equation for critical flow. We can calculate that. We can calculate critical depth. We can write it in terms of the width. And the B2 is unknown here. So taking this and doing a bit of algebra, because remember that E1 is equal to the energy at the throat. Do some algebra from here, we'll get an expression for B2. Let's see there. So E1, E1, 2/3 of the E1 gives us this this right hand side. So let's put that in here. Equals 2 times E1 over 3. We don't need these brackets, but I'll put them in anyway. B2 crit, I'm just going to calculate using that formula there, which is equal to, I'll use a square root function because it's convenient, the square root of capital Q squared divided by G divided by what we've done, this 2/3 E1 to the third, so just above for convenience, all that to the 3, sorry, not the third, close brackets, and we get 2.16 meters. Okay, it's got narrower, that's what we'd expected. It's got narrower, it was at 3 meters, yeah, so looks sensible. Y crit, well, we can always calculate Y crit using our formulae, one of these two on the right hand side, brackets, I'll do it with the Q squared and the new B, so Q squared divided by this new B squared divided by G, all to the raised to the 1/3. So the Y critical is 1.103 in this throat. Now it's different to the Y critical upstream because it's got different width. Okay, part 1 was asking for that critical width. Part 2 asks us, say, what happens when the contraction is less than this critical value, 2 meters. What is going to happen is that, well, we need to decide what will happen with this depth, but we'd expect, as it's got narrower, we'd expect this height upstream to increase a little bit. So let's see. So B2 is 2 meters. B2 is less than the crit of 2.16. Y2 will actually be equal to the Y2 crit which we've just calculated, because it can't drop below that. So we'll just choose the 1.103. Okay. that's not correct. Y crit is actually based on this this width, so let's try this calculation for y crit. So it's equal to 1/3 of q squared over 2, and q, well, we'll do it with that, like q squared over 2. So in fact, let's just make this a bit more clear. I'm going to insert cell to move this lot down. I'm going to put a Q2 calculation in here, which will just make my calculation easier, which will be capital Q divided by the width. Let's make sure we've got units okay. Just copy the units, keep it clear, keep it consistent. Right, so now y2c is just this formula. It equals brackets q squared, lowercase q2 squared over g, all raised to the 1/3. Okay. Now, it says what will the y1 be when with y2 when b2 changes or it's less than the critical. Well, we have this formula, the basic formula, that energy approaching is equal to the energy in the throat. Energy at the throat is E2 crit, so it's equal to y2c. So we can write this formula here. This is a little bit different to when you've got a bump in there, but it's y plus v squared, y1 plus v1 squared over 2g is equal to the energy at the throat, okay, which is 3 over 2 y2 crit, we've just calculated. The unknown in this expression is the y1. If we do a bit of algebra, we'll get this expression, which is slightly wrong there. It should have a cubic there. We get this expression for y1 in a cubic that we need to solve. Okay, so A being 1, B being this expression, C being 0, and D being this expression. So let's try that. A is equal to 1. B is equal to minus y2c times 3 divided by 2. C equal to 0, and D is equal to actually it's Q2 squared, Q2 squared divided by 2 divided by G. No, it's not that. Forget that one. It's equal to Q2 squared. Squared divided by B1 squared to get a lowercase q divided by 2 divided by g. Well, we can put those numbers in our quadratic solver. Let's just take those numbers here. And we can't take those. I'm going to go to our cubic solver, not quadratic. I'm going to paste these into here, and we see that there's going to be a solution a bit less than 0.05, one at just about 0.5. Actually, there's no third solution, so we need to sort of adjust this graph to see where it's going to be. 0.1, I'll try in there. Okay, yeah. So it's going to cross around 1.6. So that's probably where we're going to go to. So it's either between 0.53, only we see that we've got a solvers here, it's getting at 0.53, those not correct, we can take those out, they're not done automatically, but we'll see that this one is 0.537. We can try some other values here, 1 and not, yeah, that's 1 and 2. Yeah, that's gone down to 1.609. That's a bit better, 1.606. And the other one is negative. We're not so bothered about it, but let's try minus 0.5. That's converged to minus 0.403. So the answer we're going to look for getting is that 1.606. The secant cubic solvers calculated that top one, but we can change these parameters to try and get the higher one. Yeah. And the automatic get highest cubic depth function has calculated 1.606. Let's go back to our contraction. The secant solver there is calculated 1.606 as well. So we can put in here 1.606 is what it's calculated. The other y1 is the equal to the 0.537, which it's not going to be because that'll be below critical. Okay. So essentially that's solved that problem, solved that question. 1.606 is what this height rises to. Started off at, remember, 1.5, and this width is 2 meters. This will rise to 1.6. Let's just have a look at how we can represent all this on our energy curve. Right, we've got all the data here. It's set up. We've got the 45-degree line here. If I clicked on it, it's not letting me click on it. Okay, so it is letting me. There it is. There's the 45-degree line. There's another line there. That's the E1 data solution. Let's have a look what we've got here. C16. That's the initial data. Energy. C16. So we've got that value in there. The second value was the energy at the. So let's draw the curves. These makes more sense to draw the curves. So we look at the formula for the curve. We've got y plus v squared. This whole expression there is v squared based on that y divided by 2g. This is the for energy when the width was in part 1, where it was 2.16. and that's the energy at part 2. So these formula I've got in there already, we can drag those down for they're not working as they should. Drag those down to draw the chart. Okay, so what have I got on this chart now? Let's zoom in somewhat. We see, let's click on the chart, we see the first, that's the energy upstream, the energy curve upstream. The blue line, the light blue line, so is the energy curve when we've got critical depth at the throat. We'll see the critical depth going into the contraction, critical depth at the contraction when we've got it equal to the critical depth, and then we see that this yellow line and green line cross at the inflection point, at the turning point, sorry, of the curve of the energy curve. Now the dark blue line is the second part of the question, where the channel is narrower than critical, and we see we have a critical depth slightly higher at the turning point of the curve, the energy curve for the 2 meter. Okay. We could look at this chart and actually draw a further line going up from that point where the dark blue and the brown line cross up to a point here which is at about 1.6 meters. So that's a further graph that you could put on there. Okay, we'll finish that.